Sometimes when we use substitution, we're not going to be able to get it exactly as we need. We're not going to be able to use one of those general integration formulas. So with those, what we do is we end up having to do something called change the variable. So we're going to have to change the variable. So instead of integrating in terms of x, we change everything in terms of a different variable to integrate. And then we'll be in a format that where we can use our forms or our rules from section 5.1. So how do we do this? Well, let's look at example 6. Find each indefinite integral. So notice if I were to let u equal x plus 6, well, my derivative du would equal 1 dx. Well, that's great. We can get rid of this, we can get rid of this, but here we have this x that isn't going to go anywhere. So we end up with an x left over times u to the 8th du. So because we have this x left over, we're going to have to do what's known as a change of variable. So what we're going to do here is we're going to say, okay, well, I need to get rid of my x here. So since I need to get rid of my x, what I want to do is here, I'm going to solve that given equation, u equals x plus 6, for x. So if I subtract 6 from both sides, u minus 6 is equal to x. Therefore, I can rewrite this problem as u minus 6 times u to the 8th power du. And now this is something I can integrate. I first need to distribute this u to the 8th to both of my terms. So it becomes the integral of u to the 9th minus 6u to the 8th. But now I'm in the format to use those rules from section 5.1. I have the power rule for both of these. Here my n is equal to 9. Therefore, I'm looking at 1 over 10 u to the 10th. 6 is a constant multiplier. It multiplies along. Here my n is equal to 8. So this is times 1 over 9 u to the 9th plus c. So then I know that I want to do two things. I want to put this back in terms of x's, and then I'm going to clean up where I can. So this becomes 1/10. Remember, u is equal to x plus 6. That gets raised to the 10th power. Here between negative 6 and 1/9, when I multiply and then I reduce, 6/9 reduces to 2/3. And then my u again is the x plus 6 raised to the 9th power plus c. So sometimes we have to change the variable of our problem, then do a little bit of algebra in order to use our basic forms from section 5.1. Let's look at example 7. So this is really the same as x over x plus 1 raised to the 1/2 dx. So we know typically what's being raised to the power is what I let u equal. Well, if u is equal to x plus 1, then the derivative du would equal 1 dx. Well, that's great, but what I don't get rid of here, I get rid of my dx, I get rid of my x plus 1, but what I'm not getting rid of is the x. So in order to get rid of that x, I have to change the variable in this problem. So I'm going to have to solve this for x. So solving for x, I end up with u minus 1 is equal to x. Putting it all together, this becomes the integral of x is equal to u minus 1. X plus 1 is u, and I'm raising that to the 1/2 power, and my dx is equal to du. Well, I can work this problem out, but first what I need to do is I need to stick each term in my numerator over u to the 1/2. So then this becomes the integral of u over u to the 1/2 minus 1 over u to the 1/2 du. And if I simplify this so I can use my rules, well, u over u to the 1/2 reduces to u to the 1/2. And 1 over u to the 1/2 is the same as u to the negative 1/2 du. Well, now I'm just using my power rule. I know that here my n is equal to 1/2. So therefore I have 1 over 3/2 u to the 3/2 minus, here I have 1 over 1/2 u to the 1/2, because my n here is equal to negative 1/2 plus c. So finally, all I want to do is clean this up and then replace all of my u's with what u is equal to, which is my x plus 1. Therefore, I end up with, well, 1 over 3/2 is equal to 2/3. Again, u is my x plus 1, and I'm raising that to the 3/2 power, minus 1 over 1/2 is 2. Again, u is my x plus 1, and I'm raising that to the 1/2 power, and then all of that plus c. So sometimes it's going to take a little bit more work than just a straight substitution to solve our integrals. So for the next few examples 8, 9, 10, and 11, we're just going to look at finding the indefinite integral. So we're not going to know whether we need to do a little bit more work or if it's straight just use substitution. So let's go ahead and take a look at all of these problems. So for number 8, I have the integral of x cubed times e raised to the x to the 4th plus 1 dx. Well, recall when it's e raised to a power, you typically let u equal to that function. So if u is equal to x to the 4th plus 1, then my derivative du is equal to 4x cubed dx. But the problem is I don't have a 4x cubed dx. I just have an x cubed dx. So what I need to do is I need to divide both sides by 4. Remember, there's an implied 1 here. So then I know that 1/4 du is equal to x cubed dx. So if we were to rewrite this, we'd end up with the integral of e raised to the x to the 4th plus 1 times x cubed dx. So then this becomes the integral of e. Remember, x to the 4th plus 1 is u. And then my x cubed dx is equal to 1/4 du. And now I'm in basic form and I can use my rules from section 5.1 to find the integral here. 1/4 is a constant multiplier. It multiplies along. And the integral of e to the u du is e to the u plus c. So finally, instead of writing u, we want to write what it is in terms of x. Therefore, this is going to be 1/4 e to the, recall u is your x to the 4th plus 1, plus c. Let's do example 9. So example 9 is 1 over x, natural log of x dx. This one's really tricky. Do you agree that we could rewrite this as 1 over x times 1 over the natural log of x dx? That's the same problem, right? Well, the reason that I want to do that is because, remember, we need to have something where the derivative exists in the problem. That's what we're doing when we're doing u substitution. So now if I let u equal what's here in my denominator, if u is equal to the natural log of x, well then the derivative du would equal 1 over x dx. Well, I have a 1 over x dx. Perfect. So then this becomes the integral of, if I rewrite it as 1 over the natural log of x times 1 over x dx, we're looking at the integral of 1 over u, and then my 1 over x dx is my du. Well, that's just one of those basic rules that I know from section 5.1. This integrates as the natural log of the absolute value of u plus c. Lastly, I don't want my answers in u's. I want my answers to be back into x's. So this then in the end becomes the natural log of the absolute value. Instead of u, I write the natural log of x plus c. So the integral of 1 over x natural log of x dx is equal to the natural log of the absolute value of the natural log of x plus c. Let's look at number 10. Number 10 is x squared plus 1 squared dx. And number 10 is very tricky as well, because for number 10, if I let u equal x squared plus 1, the derivative du would equal 2x dx. And the problem is that we don't have another x there. You are not allowed to divide an x term. You can divide by numbers, but not by variables. So I can't do this problem by u substitution. There's got to be a different way to do this problem, and there is. If I'm squaring something, that means I can just write it twice and FOIL. So if I write this twice and FOIL, I end up with x to the 4th plus x squared plus another x squared is my 2x squared, and then plus 1 dx. And then I can use the rules from section 5.1 to integrate this. So here my n is equal to 4. Therefore, I'm looking at 1 over 5 x to the 5th plus 2 is a constant multiplier. It multiplies along. Here my n is equal to 2. So then this is times 1 over 3 x cubed plus, this is a constant, that's a k, so that's going to be 1 times x plus c. And in the end, all I can do here is place these two on top of each other. So this is 2/3 x cubed, and I don't really need the coefficient of 1 plus c. Right, number 11, the last one in this section, is x squared minus 1 over x cubed minus 3x plus 7 dx. Now recall, if there's something in the denominator, you're going to try to let that equal u. So in this case, u is equal to x cubed minus 3x plus 7. If u is equal to x cubed minus 3x plus 7, that means the derivative du would equal 3x squared minus 3 dx. But I don't have a 3x squared minus 3 dx. I have an x squared minus 1 dx. Well, if I were to divide the 3 out of all of those terms, I would end up with 1/3 du is equal to x squared minus 1 dx. Great. So then this, recall, can just be written as the integral of 1 over x cubed minus 3x plus 7 times x squared minus 1 dx. Therefore, when I'm substituting, I know this is going to be 1 over u times 1/3 du. Well, the integral of 1 over u du, that's just one of those basic forms that I know from section 5.1. Therefore, I'm looking at 1/3 times the natural log of the absolute value of u plus c. And the last thing I do is I get rid of my u's and put my x's back in. So this becomes x cubed minus 3x plus 7 plus c. So the integral of x squared minus 1 over x cubed minus 3x plus 7 dx is 1/3 times the natural log of the absolute value of x cubed minus 3x plus 7 plus c. That's it for section 5.2.